Okay, guys, are we live? I think we are. Okay. Let's wait a couple of minutes for people to get around. We're going to go through some parts of the paper that are relevant for dataset preparation for the NLLB model. So we're going to skim a little bit through the paper and also download some data, try and do some filtering, do some processing, and then we can kick off maybe some smaller run and see how everything goes. Make sure we can run stuff end to end. That's going to be the goal for tonight and for tomorrow. Okay. Let me know if you can hear me, guys. Let me also paste the link to Discord server. Here is the link. Just came back from a workout, so I'm just drinking some suspicious fluids. Let me find my Discord here. Let's go to the Meta NLLB replication channel. Stream just started. Okay. I see some people are already here. We can slowly start, guys. I want to go through the rest of this section on preparing the data set. So let's see what I do when it comes to deduplication. Training data duplication is critical for large model training, important for machine translation as well. They remove the duplicates. In order to determine if two texts are duplicates, we apply a normalization process. Removes punctuation, unprinted characters, and replaces all digits. The filtering can remove pair duplicates, defined as cases where two data points have identical source and target, or source-target duplicates, i.e. data points that have the same source side but might have different targets, and vice versa. Source deduplication is useful for back-translated data to catch cases where the back-translation model decodes to the same sequence regardless of its input. Target deduplication is useful for mind, where same source sentences are aligned with multiple target sentences. Okay. Okay, here they show that adding the mind and back translated data, all of this helps significantly. And it looks especially for non-English directions. Okay. The effect of filtering is discussed in the section 733, where we experiment with training bilingual model with 6 directions. Can you link this paper? Yes, I can. Thanks a lot, Navjot. Okay. Let me know if you can open it. Otherwise, check out the. I pasted it in the Discord server as well. Okay, the effect of filtering is discussed there, where we experimented comparing their performance. The results in table 27 confirm the filtering leads to an improvement in performance as well as reduction in toxicity. The filtering configuration is made available along with other training scripts. Sounds good. Okay, let's continue here. We trained dense 3.3 built-in transformer on 3 sets of data, only primary in mind, and then back translation. And the results can be seen in the table figure 34, which we just saw. We demonstrate the impact of adding different data sources over primary data. Low resource languages improve more compared to high resource. Let's see that again. So low resource compares more, relatively speaking, than high. And very low, even more. Same here. Okay. Looking deeper at the results, we investigate how mined and back-translated data sources impact very low. We define very low resources language with fewer than 100,000 unique sentence pairs across all language pairings available in public bytext corpora, with 84 total. Okay. So does that mean like any direction that has either as a source or target that language, if we don't have at least 100,000, then that's very low? Okay. We observe the benefits. They prepare the final data set. The dataset comprises primary bytext for 661 language pairs, mined bytext for 784 language pairs, and 261 for back-translated bytext. In total, there are 1,220 language pairs. And these directions sum to over 18 billion total sentence pairs. Okay, let's just kind of note that down somewhere. One 816. Okay. Let's continue. Preparing the model. Okay, so we skimmed through this data section. They never mentioned the details, the exact details behind how much data how they think about. So we read this whole 8.1 section basically. We didn't see the details behind how they think about how much data do they need for each of the models they're training, depending on the scale. That might be some tribal knowledge in the MT community, but I'm unaware of it, if there is such a thing. Let's maybe see preparing the model section. Sparsely scaling model architecture. Designing an optimized training curriculum. We might have some details about the data here, because what they do is they take the lower resource language directions, and they start adding those only later at the end of the training or something like that. And then that allows them to prevent overfitting that would happen if you were to immediately include that data. training details, performance. Let's just quickly skim and see what's going on here. Performance, human eval. Okay, so this is just the evaluation. Let's see. Let's skim through the training details. We trained the model for 300,000 steps using the 4-phase curriculum described in the previous section. We use an effective batch size of 1 million tokens per update. Okay. Let's just note that somewhere. My Notion is becoming a mess, so I'll have to just rearrange and start writing down everything in the same page. So 300k steps, 4-phase curriculum, 1M tokens per update, effective batch size. The maximum sequence length during training is 512 for both the encoder and the decoder. Okay, sequence length 512. They use Atom. For training efficiency, we use memory efficient FP16. And also maintain Atom optimizer states in FP16 will linearly increase the learning rate from, okay, for 8,000 steps. Inverse square, cross entropy, the label smoothing. Additional load balancing loss as described in the section. Okay, this is more for mixture of experts for the final model. I'm not sure whether this is, I'm not sure whether this is the training result for the smaller dense checkpoints. Not sure. Let's see. Just double check that. Experimental setup. Results. Okay, let's kind of skim through this section as well. No curriculum. Curriculum with native bucketing based on training example counts. Curriculum with bucketing into multiple phases based on observed overfitting when training with no curriculum. In the naive bucketing curriculum of variant 2, we divide language pairs into those with more than 9 million training sentence pairs, those with fewer than 9 million, okay? And we begin training with the language pairs with more than 9 million sentences. At 200,000 updates, we then introduce language pairs with fewer than 9M. Okay, chosen empirically. And then there's the phased curriculum variant. We first train a model with, so let's add that fact that we need to have basically phased curriculum. We first train the model with variant 1, no curriculum, and then divide language pairs into n different buckets based on when they start to overfit. Then we restart training, introducing a particular bucket at a certain number of steps, median number of updates, after which all directions in the bucket start to overfit. In our particular instantiation, we set this to 300k, 130k, 70k, and 30k. Pairs are introduced first at the start of model training. Pairs in B1 are introduced at this step, and so on. Okay. The exact composition is explained there briefly. There are 822 pairs with 673 low resource pairs in B0. Okay, there are 506 pairs. Okay. And then here they just show that improves the results. So that's a 4-stage, how did they call it? I think four-phase curriculum. 4-phase curriculum is the name. Okay. Let's continue. I'm kind of going reverse direction. Okay, this is just some. We can ignore that. We'll probably be reading the paper on and off during the next days, just to pick up all of the details, make sure that the settings are also the same as in the FairSec NLLB branch. In the previous section, we discussed how we improve. Okay. How do we scale and adapt the model architecture? Just want to skim this. Okay. Nothing of interest there because they're just focusing on mixture of models model. We want to focus on, for the time being, we want to focus on dense transformers. Okay. So page 90. Let's now skim down there. Let's see whether we skipped anything else that's interesting. That's how I usually read papers. Just I already have some heuristics built in, so I know what to focus on, what to ignore. It's hard to verbalize all of that though. Results on floors. Evaluation. Analysis. Effect of phased curriculum on low resource overfitting. Okay. Let's see. I'm curious about this because we might be able to just play and analyze the data a little bit before we start training. We analyze several properties. We first discussed the language collocation. Per language distribution across 128 experts. Then we bed all of the trained languages in 2D with UMAP. Okay. Indo-European. Okay, so they basically embed the vectors just before we sample which experts we want to pick. And you can see there's certain languages prefer certain experts. That's the thing with, but we don't care about mixture of experts for now, nor about distillation. For that, we'd need to have bigger model checkpoints, which we don't. Language. Data challenges. Okay. I don't think anything here will be super relevant for what we need. Environmental impact. That's definitely not useful for now. Expanding. Future contributions. Acknowledgements. Okay, that's it. Let's maybe see in the appendix, maybe they have something about data. Some details about data. Toxicity lists. Okay, data. There is a significant domain mismatch between the data used to train our LID system and the web corpus the system is used on in our pipeline. We randomly picked several thousand sentences predicted to be among those languages and asked annotators to assess whether each prediction was correct. We built a challenge set based on these annotations to benchmark our final LID model. Table 50 compares the performance of our model against a readily available CLD3. Okay, nothing useful there, honestly. Let's continue. Let's continue. Let's continue here. Okay, preparing the data. This might be interesting. What's this empty data tool? They keep on mentioning this. Empty data, maybe GitHub. A tool that locates, automates the collection and preparation of empty datasets. Provides CLI and Python APIs which can be used for preparing the experiment. Okay. Empty data list. Empty data get. How to contribute. Okay. Looks like a decent tool and seems it's relatively active. number of directions, number of languages. Here we'll list the training directions available for different data sources used for training after filtering. Here we'll list the training directions available for different data sources used for training after filtering. Okay, let's open up this. Okay. Here are the list of directions used for the 4-phase curriculum. Final length pairs CL3, CL2, CL1. Got it. So they include all of that. That's cool. Performance, we don't care about performance. Toxicity, none of that matters for now. Public benchmarks. Okay. Scores. Scores. Cosine similarity scores. Model card. License. Okay. Training data, let's see here. Section 5. Let's check out section 5 after we wrap up this. So check out section 5. Section 5 data. Let's skim through these couple of pages. Okay. It contains bytext from English to other 43 languages or 6,193 sentences. This was created by professional translators. Huh. Interesting. It's actually for commercial use cases. It can be used. That's nice. Share alike. Nice. So NLLB seed is actually permissibly licensed. Okay. Okay. So some portions here are also non-commercial. And this is for the mind. We create a mind by text from publicly available web data for 148 English-centric, non-English-centric, using Stopes in Laser 3. Okay, we saw this already. Okay, so let's go back to page 90 and let's quickly skim these parts and find anything that might be relevant for us to practically train this system. Biases in list building. I think this is about toxicity. We can ignore all of this. We can ignore this. We can ignore this. Eval, we can ignore it safely. Okay, this might be interesting. Data augmentation. Curriculum learning. Conditional compute. Model architecture. Modeling. Section 5, and in section 6 we just found something interesting. So section 5 is definitely super relevant. What is section 4 about? Makes me dizzy just scrolling through this. There is a ton of content. Creating professionally translated datasets. That's 4. Languages in 3. And everything else here is just discussions. So we can safely ignore all of this. Four as well. just describes the workflow they use to basically collect floors to 100. Okay. Maybe let's start from here. There's only a couple of relevant things we have to go through. So first 20 pages we can kind of ignore. Yes, I am looking for a co-founder. I didn't see your message, sorry. I'm currently chatting with some people. I guess the best way to find the person is to just work with people and see and let it organically evolve. That's how I'm thinking about it, honestly. So it's English-centric. Translation workflow, we don't care about it. For 39 languages. While some of other languages were transliterated. Okay, we can skip this. Okay, section 5. That's where the whole information about data processing and whatnot is basically described. So let's read that. Make sure it's fresh knowledge. Automatically creating translation training data for hundreds of languages. We can skim most of these parts. I just want to extract the most important parts. The pragmatic parts. Okay, this is kind of the high-level diagram. Monolingual, public bytext, NLLB seed, and then using laser, we mine. And then we train the model. Okay. Where do we download NLLB seed from? That's an important question. Language identification. There are some challenges. Hi Amrit, what's up? Yeah, I already read paper back while I was in Montenegro. I'm just now skimming for actionable insights, and I'm extracting those into Notion page so that we can later cross-verify with the actual code in FairSec and make sure that everything makes sense. That's kind of what we're doing. Okay. language identification, filtering and cleaning, monolingual, and then we do the mining. Okay, so laser is trained using existing bytext, and then we use it to basically mine for data. Okay, this is more, we can skip the related work. Let's go here. So they utilize FastText to train language identification models, widely used for text classification tasks due to its simplicity and speed. We embed character level n-grams from the input text, then leverage a multi-class linear classifier on top. We embed character level n-grams from the input text and leverage a multi-class linear classifier. Okay, the lightweight nature of FastText enables our LID models to handle web scale data. Additionally, a linear model has the benefit of being easily explainable, allowing us to trace any classification error back to its root cause. This is instrumental in addressing common pitfalls. Okay. Classifier design. I didn't see this FastText implementation anywhere, although we probably won't have to care about this because we found earlier today LNAI's reconstruction of the bytext, of the mined bytext from the NLLB paper. They just followed the open source metadata information, scraped that data, and released that on Hugging Face Hub for those of you who missed the previous stream. So we have the mined data that makes stuff, that makes life much easier. So let's see what they do here. A combination of multiple binary classifiers where the final decision is obtained by selecting the language having the highest score after a threshold is applied. Okay. And then a multi-class classifier using softmax. Okay. Second, we found that this approach generally is better to out of the main data, which is our primary use case, because I assume FastText was what they train on Wikipedia and then they try and do inference on web scale data. Okay. And finally, a single classifier has the added benefit of being computationally simpler, thus streamlining the language ID process. Okay. They just use some temperature manipulation to balance for the class imbalance of different languages. Okay. I'm not sure, I've never seen these models in their repository, so I'm not sure where do they release those, if they release them at all. Okay, our best model was trained with softmax loss over 2 epochs. We discarded words with less than 1,000 occurrences after upsampling. Okay. Yes, we do have mine data. We just have to download it. It's like 450 gigabytes of data. And it's permissively licensed, by the way. Okay, so they have some LID inspection interface. Okay, filtering the training data. So this is important. It's good to cross-check. We're gonna cross-check this filtering here, the settings here, with FastText settings in YAML configs that they have. To mitigate the learning of spurious correlations due to noisy training samples while modeling hundreds of languages, we worked in collaboration with linguists to develop several filters illustrated in Table 3 and described below. All are subsequently applied on our raw training dataset. So that's going to be the first thing we're going to do this here. So after we download a ton of data using their provided scripts, we're going to call this filtering method. And then we're going to do some binarization and using the SPM 200. And they're also going to shard the data because we have a ton of data. Okay, different ways of filtering. We computed the character distributions of each language on our development set and defined an arbitrary accepted character set for each of them by considering all characters falling within the first 95th percentile. We consequently filtered out any sentence from our training set that was composed of less than 80% of such accepted characters. Okay, that makes sense as a heuristic. So the model cannot be used for commercial purposes, but the data, the part of the data sets which LNAI has released is actually looks like it can be used for commercial purposes, but the checkpoints cannot. So we still have to train the models and release the checkpoints. Okay, I didn't see this character histogram filtering in the, so let me show you what I mean. If we open up FastText here, let me see just a second. Here's Stopes. Here is the filtering script. And this is the filtering config, I think. So let's see whether they have normalization. Train primary. LID filter. Length, dedupe, LID, let's just see where is this? Okay, we're gonna find it a bit later. Included corpora, DTube filter. I'm trying to find a directory that's called like this, train primary. I don't see it. Okay, oops. We'll try and find it a bit later. Let's get back here. So there is a character. Let's kind of scribble down some of these filtering methods they're applying. So training details, filtering details, character histograms. Okay. Script detection. For languages whose script spans thousands of characters, the character histogram method mentioned above was not as effective. Okay, since the character distribution trends were less prominent. As an alternative, linguists provided Unicode ranges to define accepted character sets. Any sentence containing less than 50% of characters from that set was eventually discarded. Okay. For example, the sentences shown in table 3 for Japanese and Chinese do not contain the right Japan enhanced script. Okay. Let's see the examples here. So is this filtering only for the LID dataset? Filtering the training data, LID, improving LID with linguistic. I think this is, yeah, this is probably less relevant because this is mostly for LID training. Still worth understanding it a bit. So here is an example of sentences that are not. This is like English sentence, even though it says here NLD. Same here. And then this is a combination of digits and English and I guess Chinese. Okay. English specific filtering. Linguists also pointed out that many mislabeled training were actually plain English sentences, as above. This can be explained by the massive prevalence of English on the web, even on pages primarily written in other languages. We built a simple, dedicated binary FastText classifier to filter these samples out of our training dataset. Makes sense. And then finally the results. that this model is capable of handling 200 languages. Okay, we can ignore the evals. Okay. We notice that predictions tend to be more robust for long sentences. Okay. Okay, that was just LID, section 5.1, language ID. Let's go to section 5.2. And then let's see how many more pages do we have here. 5.3, mining. And we can skip, I think, a ton of stuff there because it's just related work and stuff. Okay. Let's go here. Let me maybe in the background just kick off some downloads. While we are doing this, we can easily run some of these methods, and later we can kick off some filtering and dataset processing tasks. Okay, so let's see which ones can we kick off here. Let me just think for a second. 22.4 gigabytes. And this is what? Turkic languages. Yeah, let's just download some of these. I already have this one, so let's just kick off download of this one. Maybe just a second, we have to specify the right config. Download. Just a second, where is the launch JSON? Is code. Direct train, fine tune, generate, interactive, and okay, I think we can just kick off a run here. And we'll store that data here. NLLB data, all good there. And let's just download that data set. Okay, gsutil not found. So that means we have to download. Can I just install that in Ubuntu simply via apt? Just a second, why do we need gsutil here? Okay, because it's using it here. Let's see whether there is some other data set that we can kick off while we are reading the paper, and then later we can handle. Okay, this is using requests library. I think we can just kick off this. Okay, looks like this one will not fail. And later we can install the gsutil. I have it on Windows, I didn't install it on Ubuntu yet. Looks like this is running. It's downloading something, I guess. Let's continue reading. Section 5.2. Monolingual data is a valuable resource which can be used for a variety of downstream tasks. They decided to extend the work done in CCNet and CC Matrix. Okay. We begin with web data as our starting point, provided by Common Crawl and Paracrawl. This data has been pre-processed. Okay. We refer to them as paragraphs. To convert the raw web text in paragraph form to sentences, we apply language identification in a hierarchical fashion. First, we apply LID to each web paragraph. Subsequently, we use the predicted language to choose a sentence splitter for the language. Okay. Makes sense. So they use the previously trained, I guess, LID model to cluster sentences into different language categories. I'm not sure how to parse these sentences, these charts, I guess, for this particular language. With this script, Latin script, LID scores tend to be skewed towards 0 or what? Hence that spike, yeah. Okay. I don't understand this part here. Our development set could not be utilized to tune the detection thresholds of our FastText classifier to a desired performance level. There is a lot of knowledge here. Like, I don't know how paracrawl was, for example, constructed. We choose. Okay, it doesn't even matter that much for now. I wonder whether they reintroduce the URLs after they've removed them. We know that these ratios should differ between languages and are not universally applicable. In certain languages, concepts may take more words to convey, meaning that setting a length-related threshold is problematic. And then I think they do some normalization here. So similarly, other languages may utilize more punctuation or have shorter words. Thus, we do not set extremely stringent filters, and we examine the amount of text filtered across all 200 languages for each of the filters. Table 8 provides some typical examples of filtered sentences. Hashtag gym girl. Exceeded numbers ratio. Document is French, yet the particular sentence, best veto ever, this looks like English. Okay, low LID threshold. The margin-based criterion requires unique sentences, but a sentence splitting and cleaning process might generate a lot of duplicate content, so we run a global deduplication process over all sentences of the same language. Language model filtering. In practice, it is difficult to train high-quality language models for low-resource languages. This is something I'm very, very interested in. For different languages that are non-English languages, create high-quality LLMs, and that's why we went through the polyglot Korean model paper yesterday, as well as the Japanese LLM that Stability AI announced a blog on. Processed around 37 petabytes of data. Wow, my God. Through the whole pipeline. This was a challenge for data management and disk usage. In particular, we had to make hard decisions when filtering high resource languages to artificially keep only around 30% of data from the most voluminous languages. This threshold was identified as the limit under which the LM score would identify sentences of low quality. Took several months to be able to get the final monolingual dataset. Go brr. We realized that processing such volume of data is not always possible and are open sourcing much of our results and code to make it easier for everyone to benefit from our effort. My God, 37.7 petabytes. That's a lot. for a single project. I mean, they are surely reusing the results, but crazy. And here I am worrying about 450 gigabytes of mine data. Let's just see whether this thing downloaded. I think it did. Okay, all good there. Let's continue with some other languages. Let's try this one. Okay, that was fast. And that was fast as well. These are smaller probably than some of the above ones. Interesting. So it turns out the first one that doesn't work with gsutil is the biggest one. Okay, this one is a bit bigger. Let's continue reading the paper, and then later we can. Okay, Amrit, what's special with the 450 gigabytes? Part of the entire data which is licensed. No, that's the mined byte text from LNAI that I mentioned previously. Okay, monolingual data at a glance. We started with 107 billion paragraphs from the web. And they discarded 2.8 billion sentences because of LID, script mismatch, or low LID score to produce 43.7 billion monolingual sentences to feed to the mining. $21.5 billion are in English. Okay. Low resource, raw data, clean sentences. How come do we have more clean sentences than raw data here for low resource? What does that even mean? Not sure. But it's not that important now. Just go to section 5.3, mining byte text for low resource languages. Okay, we can skip this. We can skip this related work. We can skip this. Maybe I can, let's see this. This seems more practical. I just had a workout before this streaming session. I ran 5 kilometers. I've done some handstand, some pull-ups, and then had some healthy meal, supplements, and I'm back. But this is almost end of the day, so like almost 11 hours of streaming. I'm slowly getting super tired. But I can push through it. I can still be productive even though I'm tired. Our student encoders used a 12-layer transformer, hidden size of 1024. No worries. Totaling around 250 million. Okay, this is how the laser 3/laser 2 was trained. Okay. So student encoders handle the lower resource languages, 148 of them, and then the trainer model actually supports higher resource languages, and those are called laser 2. So we've seen that over the past few days. Proxy metric for new encoders. Here we've seen this as well. Yeah, this is implemented in the laser repo, this xsim function. You can check it out. We've done that over the last couple of days. We stepped through the code actually. For these NMT baselines, we do not apply additional filtering on the bytext and leave this to the training procedure of our massively multilingual system. Thus, the translation performance is compared to training the same NMT on existing bytext only. Okay, they're just showing how the performance of the NMT systems get better as we use the mine data. Language-specific encoder training. Okay, they reuse the CC matrix bytexts for some of the languages. We've seen that before also. Improving laser. I think we can skip over all of this. No, Amrit, that's completely different thing. So 37.7 petabytes refer to their monolingual datasets, and 450 gigabytes refers to the mined data. You get a lot less data when you do the mining, because you'll have to ditch many of the sentences they don't have any pairing. There is no translation in your target dataset. There is a big funnel that happens from monolingual to mined bytext, basically. Okay. Handling specific scripts. Okay, mining at a glance. They reuse some stuff from CC Matrix as well, so that's their previous work from Meta. Limitations and conclusion. So they nowhere in the paper do they actually mention the specific details behind how much data do they use for smaller checkpoints. So there is obviously the mixture of expert, the big one, the 54 billion parameter model, but there are also the 3.3 billion dense checkpoints. They never mention exactly how they train it. So I guess we'll just have to experiment a bit. That's what I was looking for, by the way, going through the paper. Let me quickly see whether this is done. Let me just download a couple of these while we are reading the paper. Okay, I didn't expect all of these to be so small, whereas the first one is 24 gigabytes. We basically downloaded all of these datasets. There are 3 more in the README that I didn't include here. and that's pretty much the primary. That's the primary data set they use. And then there is a 450 gigabytes of the bytext, of the mined bytext. And finally, this one. Okay, guys. So we're just left with this one, which is failing due to the gsutil. We have to install gsutil. Okay, let me just add that as a to-do quickly. Okay. Okay. Just adding some notes. Let's wrap up this section. We know that for some languages, we're only able to create a small amount of bytext through data mining. Limiting factor is predominantly the lack of even monolingual data. Fun fact, I think that Swedish Wikipedia is mostly translated using machine translation. There is some bot that basically has done that whole translation. And there's one more language that you've never heard of that has more data than, that's like second, it has the most data after English on the whole Wikipedia. Yeah. Okay, conclusion. Okay. We're releasing all the code that was used to train the LID model. I haven't seen this. LSJ bot. Yes. Something like that. I'm not sure why they've done that, nor why did Wikipedia allow that to happen? Don't they have some type of curation rules disallowing bots to just translate stuff? Okay. And I've seen one more interesting part here, I think section 6, and we are done with the paper. We can go and figure out the GSUtil installation and start preparing the primary data set. I might even download the whole mind corpus just to play a little bit locally with it. Although ultimately we won't be able to obviously run that much data on my machine, otherwise it will take months to train. Nor do we need it for smaller checkpoints, right? Motivation is so that, I mean, to facilitate research in low resource, basically, for low resource languages. That's kind of one of the motivations, I assume. I mean, sharing the work is a common practice. Used to be before the ChatGPT era started. Okay, let's kind of skim through this. Let me quickly skim through section 6 just to see what are the main subsections here. Okay, so there is the human eval, NLLB seed. That's something I want to read, the 6.5, 6.4 as well. .3 maybe. .2 we can skip. Okay, so maybe we'll go through a couple of those sections. Let's just see here. To tokenize our text sequences, we train a single sentence piece model for all of the languages. We sample a total of 100 million. Okay. We went through this. My girlfriend just entered the home. Model architecture, encoder, decoder. Okay, there's a couple of interesting things to note here. The prefixing with the language token. I think we want to read that one. Decoder transforms the source token sequence into a sequence of token embeddings. The decoder attends to the encoder output and autoregressively generates. Okay, standard stuff. And then they say note that we prefix the source sequence with the source language, ls, as opposed to the target language as previously done in several works. This is primarily because we prioritize optimizing zero-shot performance. Okay. When the source is conditioned on only the source language, the encoder generalizes better at two pairs of source and target languages not encountered during training. Okay. They have some ablation dataset as well. Let's see what that one is. We construct a multilingual machine translation benchmark such that it is representative of our final benchmark of 200 plus languages. We chose a representative subsample of 53 out of 202 languages. I don't think they've shared the ablation dataset. Okay, we can skip the part with mixture of experts for now. Some regularization methods they use there for the mixture of experts model. Curriculum learning, we went through this. The 4-phase curriculum. Okay, self-supervision. We might have to do something like this as well, so it might be useful to read through this. So self-supervision strategies. SSL. Just a second. Let me see how many of you are here, guys. I see 10 people. Eight people watching. Nice. How are you guys doing? For low resource languages, there is generally a limited or no bytext data available. In case where bytext data is publicly available, the domain of the available data could be narrow. Hey, what's up, Asim? In addition to bytext mining. Okay, so in addition to bytext mining that we already saw, another way of leveraging the monolingual data, so that's 37.7 petabytes originally. So we got that data from the raw 37.7 petabytes, and now we are additionally funneling it into mined bytext dataset, and we also leverage that filtered monolingual dataset here as an SSL task, basically. So they study a couple of different tasks: language modeling objective, denoising autoencoder objective, so I guess that's like something like BERT, and then the combination of both. We followed that up with studying the optimal curriculum when combining the task of self-supervised learning on monolingual data along with the task of training on multilingual machine translation on bytext. We use the recommendations from this study to decide on our self-supervision strategy for our final model. Okay? There are different ways of incorporating self-supervision. Okay. Different strategies. Classical LM objective. We use the multilingual denoising autoencoder objective for self-supervision on the multilingual text corpus for languages in our ablation benchmark. Baseline is TENS 1.3 billion model trained for 100K updates on the MMT task with a sampling temperature of 1. We train the SSL task variants with the same architecture and sampling temperature for 200K steps to ensure that SSL task variants are exposed to as much multilingual parallel data as the baseline. Three options: retraining on SSL followed by fine-tuning on MMT. So denoising autoencoder. We train on SSL for the first 100K, followed by yet another 100K on MMT. Or multitask on both of them. And finally multitask followed by fine-tuning. Results. This hurts performance, the first option. There is a fundamental mismatch in the two training tasks, and it is hard for fine-tuning to recover from the initial state at the end of pre-training. Okay, so basically we want to do multitask with SSL and MMT. Actually, this one is the best one, right? Although very comparable. We train all SSL task variants in this section in a multitask learning setup. Okay. So again, MMT plus the denoising autoencoder. Wait, what's the difference between this analysis here and the previous one here? Okay, this is just a curriculum. And And here they try multiple objectives at the same time. Okay. SSL, let me just make a note. We want to do something like MMT plus DAE. Okay, and the final section, we are done with the paper. Let me just see what else is here. Okay, there is also the NLLB seed. Okay, a couple of pages here. These models are expensive, so they use traditional phrase-based statistical translation model. Table 20. Primary, mind, series of bilingual Moses models. Okay. Okay, they just try a bunch of combinations here. And results are in table 21. Okay. Let's quickly skim through this as well. We report the performance of the baseline model using only primary data, and then the other three models trained by incrementally augmenting the training data with the mind and back translated data sets, back translation data sets. We observe that the highest performance is achieved when using all sources of data. I wonder how much of that is just because of additional compute versus the quality of the qualitative nature of data. If you just had more mind instead of adding back translation data, would you get the same results? I suspect you would. Yeah. We can further probe into back translation quality by looking at the performance of our two teacher models, the MMT model and the set of bilingual SMT models. Which are trained on the same primary and line data. In table 22, okay, although the average performance might be low, we hypothesize that the combination of different complementary sources of noise is the reason why its addition is still beneficial to the overall performance. The differences between generations can be visualized by plotting the total token frequencies generated by the MMT and SMT when translating the same corpus. Okay, I think this is the last section, and then this one we're done. Tag back translation is a technique to help the model discern between different sources of data it is being exposed to. This is achieved by prepending special tokens to back translated training examples, and it has been shown to boost performance. In the experiments of the previous section, we used an extended tagging scheme using special tokens for each of the three data sources. We studied the effects of ablating away this tagging scheme, experimenting with using just a single tag to mark all secondary data, as well as using no tags. Results in table 23 demonstrate the benefits of using fine-grained tags. This provides further evidence to support the hypothesis of this paper that tagging is useful to help the model distinguish between synthetic and natural data. Kind of reminds me of the decision transformer paper, if you read that one. It also suggests that signaling the specific nature of synthetic data can further boost performance. Okay, let's read this section and we are done, guys. Couple of pages left. For a considerable number of low-resource languages, the parallel corpora which are publicly available often have only a few thousand sentences. They frequently come from sources with a highly specific domain, such as scripture, Bible, and the level of quality assurance is often unclear. While translating millions of sentences with professional translators is unfeasible, translating a few thousand is possible. It is important to understand whether there is value in such small but high-quality human annotated seed datasets for low-resource languages. Is such a small dataset sufficient to bootstrap an empty system for a new low-resource language, or fine-tune an existing empty system on a new domain? To investigate these questions, okay. So here's some configurations they'll be testing for. Let's see the usefulness of NLLB seed. Okay, so let's see what do they do here. We want to measure the performance of bilingual models trained on seed against those trained on publicly available as well as on the combination of both. Secondly, given a certain amount of publicly available, we studied the incremental effect of adding the seed compared to simply adding more data. Diminished plus NLLB seed. This is obtained by subtracting from public a random sample of sentences of the same size as seed and swapping in the higher quality seed data. The result is a dataset which is of the same size, but which also contains the seed. That's depicted here, so that's the diminished one. So basically public, just higher quality public. Diminished plus seed and combined, okay? Let's see the results. We select 8 low resource directions for fair comparison. Okay. We train bilingual models for each direction. Each language pair uses a custom sentence piece vocab of size 1K. Okay, results. Table 24 reveal that combined significantly boost performance, I guess. Training on the seed leads to markedly higher performance on average. So even public seed, you can see way higher. Even though this is only 6,000, it's much better results. The best performance is obtained by combining all the data. Okay, I mean, this is definitely not a surprising result. We investigate whether using NLLB seed, at least qualitatively. We investigate whether using NLLB seed might additionally affect performance when back translation is used. Okay, so basically here, as far as I understood, the back translation models were also trained on seed, and then that improved. And then you add additionally back translation data and you improve the scores, or what? Let me see again. Whether using NLLB seed might additionally affect performance when back translation is used. For example, if using a small amount of human translated data, such as NLLB seed, might increase back translation quality. We start with base models trained on public text and on diminished plus NLLB seed, use them to perform back translation, and then train a new set of models on this augmented data. Got it. Okay. That's it. Nothing else is really informative here. We don't have any practical insights other than what we've just seen. Let me just see whether maybe for a mixture of experts. Yeah, we need, I don't know, ideally we'd create some website or something where you would, as a side effect, be collecting translations. I mean, Duolingo and some of those language apps are in a perfect position to collect high quality translation data, I guess. Let me just go and see the table of contents again. Let's see here whether there is something interesting. Okay, that's it. Let's try now and install the GSUtil on Ubuntu. And then let's start playing with data. And then tomorrow we can spend the day maybe analyzing the data, filtering, processing the data, and hopefully by the end of the day, maybe even kick off a smaller run just to make sure we have everything set up running end to end. That would be super cool. Okay. GSUtil. How do we install GSUtil? So we can install it as a snap package. Any recommendations here, guys? Should we go with the snap package or install it via apt? Apt. Do I need all of this, or can I just install the gsutil? Let me just see if there is an easier way to do this. Okay, this is pretty much the same as previous one. Okay, let's just follow the instructions there. Next thing you know, somebody's gonna attack, do that recent audio attack, if you saw that one, for stealing passwords by just listening for keystrokes and using some deep learning model to basically figure out the keystrokes you're using. Did you see that one? Super scary, man. Not surprising that it works, but super scary. Well, yeah, if you control all of the mics, sometimes that's also problematic. It has apt. Do we need this? Okay. Install this. Add the gcloud CLI distribution URI as a package source. If your distribution supports the sign by option, run the following. If it doesn't, then run this. Make sure you don't have duplicate entries for the Cloud SDK repo in the lists here. I don't even have it for now. So how do we figure out whether Ubuntu is signed by, supports the sign by option? Okay, it's supported. Then we run this. Sign by Google. Okay. Google Cloud SDK list. Import the Google public key. If your distribution's apt key command supports the key ring, run the following command. Can we just, is this supported on Ubuntu or not? Looks like it is. Do we see keyring here? Keyring file, I guess it is. Okay, and then update and install the Cloud CLI. Unpacking the Cloud CLI. Okay, seems this worked. If I run gsutil, does it exist now? Okay, it looks like we have it. Looking good. Any of the following components? Do we need anything here? I don't think so. I think we can just rerun this and confirm it works now. Okay, looks like it's working, guys. Nice. We've downloaded a ton of data here. Let me just check some to-dos while this is happening. This Notion looks terrible at the moment. I have to start just collecting documents instead of just having to-dos like this. Let me just rearrange this a little bit. Work log, this was from the first stream. Data analysis, so by text. Training details. Training details. To-dos. So compute data. Just ask one question. You're just asking some questions in the Polyglot channel in Luther AI, because they, as if you were here a couple of days ago, we went through their paper Polyglot Korean, again large language model for Korean language, and also they were a part of the Japanese LLM that Stability AI released as well. So that was cool. Okay, let's see how this is progressing. 15 gigabytes downloaded already. Let's figure out these other data sets, what to do with them. I should probably download the data, the mined by text during the night or something. It will be interesting to see how my ISP will react to me downloading half a terabyte of data during the night. Okay, once we kick off this run and see how fast things complete, then we can have more information to submit some application here and see how that goes. Okay, guys, let me see whether it makes sense to start anything else while this is downloading. Maybe let's quickly see. Let's see whether we can download this data here. Files are not publicly available. To get these, we have to do what? Do we have to log in? Okay. Maybe better not to share the email. Otherwise later maybe somebody will spam me. Just a second, guys. Let me just log in here and see whether I can download anything. Okay, downloads. Confirmation instructions have been sent to my email. Let me just see what's up there. Confirm the email. Transform to Open Science. Okay, let's see what's up here. Recent uploads. Okay, so I guess now if I open up, just a second. Close access. I'm logged in, but I still don't have access to this one. So what do we do? How does one get access to this? Downloads. Closed. Files are not publicly accessible. I understand that much, but can you please tell me how can I get the data? If anybody knows if you've ever used this website or something, which is highly unlikely unless you're into machine translation. Scraping for data. No idea. Okay, let's see this other data set. We can download it, but again we have to sign in. Okay, just see. Why is the UI so messed up on Kaggle? Is this Kaggle? Sign in. Okay, I'm downloading this data. Let me just copy this path. Copy path. What's up here? Okay. I think I've managed to download this one. Okay, here it is. Here is that data set, although I'm not sure how to process it. We will open it up later. So that's this one. Eve language corpus. Eve Eng. Let me just rename it. Eve Eng. Title. And then there is this one, Lorelei. How do you get this one? Download. The pain you have to go through to get some data, it's real. Okay, do you have to be a member of this university to join or whatnot? Register, University of Pennsylvania, privacy policy. What's an LDC? Okay, Linguistic Data Consortium account. Oh my God, so much data. Just a second. Okay, the good thing is we have a ton of data downloaded here from the script. Even if you don't download this one, we're fine. Okay. Just trying to submit the form here. Okay. First name, last name, address, city, country. Okay. I think I've done it. Let me just try and reopen this. You can close all of this. Okay, guys, we can ignore this for now. Too bothersome to get a couple of megabytes of data. Yeah, I think we can wrap up for the night, and then tomorrow we can play a bit with the data we downloaded. I think I'm gonna kick off the download of the mind dataset, and then we can do the filtering and processing tomorrow on the subset of that huge dataset. So I guess that makes sense. Okay, guys, have a good night or good day wherever you are, and see you tomorrow, 10:30 a.m. roughly in the morning CET. I'm gonna start streaming again, and that's the plan. Cheers. See ya, guys. Sergey, I see you sent some messages. Not sure if this is the NDA, but just curious, while you were at DeepMind, did you have to gather data for projects you were involved in? It's mostly like, it's not NDA. Like Google has a bunch of internal data sets. You usually just have to do some internal stuff to process the existing data sets. That's it. It's very complex. There is a lot of, Google is such a complex machinery. There is a ton of internal tools, formats. It's just, there is no single answer really. I know that doesn't answer the question really in a satisfactory manner, but that's the realistic answer. That's the life at Google, I guess. Cheers, guys. See you tomorrow. Have a good night. Have a good day.